finger concept. So we can have multiple finger for same MOSFET. So yesterday you said, yesterday in the class you said that when you make the fingers, so in that case area for the circuit increases. But sir, I
Did
have
I say
observed.
that? Did I say that? No.
Sir, in the class, yes sir, yes.
I said if you use a bigger device, then the area would increase, and you will be able to make it only implement it only by going to fingers.
Yes, so I measured that on the virtuoso. So I took 8 fingers, but the area was actually decreasing, and I could see that the delays was also decreasing
नहीं तो
because of
किसका एरिया? एक मिनट, किसका एरिया?
the OD
स्टैंडर्ड
area.
सेल का ओडी एरिया की बात नहीं कर रहे हैं हम, तो सेल एरिया की बात कर रहे हैं गगनदीप.
Okay, अच्छा.
So as you go to more fingers, your cells will become wider, is it not?
Yes sir.
है ना? Height is fixed and your cell is now wider, so area increases.
Uh, but the
Sir,
height decreases in that basically.
No, standard cell height is fixed. We agreed that, na?
Okay, yes. With respect to standard cell, that
Standard cell height is fixed. You make all the bricks of same height, na? That was what we had agreed.
but the delays would decrease because OD region is smaller now.
We don't know, because then you will now need to route extra metal. Metal capacitance will start to come into picture.
Oh yes. So I will.
Then there will be poly resistance. अभी तक हम बात ही नहीं कर रहे हैं poly resistance की, but there is, see, we are making such thin poly lines. There also it is not metal, it is poly. Poly is resistance. So poly has some resistance. So there is some gate resistance also that comes into picture.
Yes, sir. So I have put that NFING option in the LDO, and I made the fingers to 8. So basically, the delays were decreasing because right now I'm not considering the post layout simulation, right?
Yeah, but इसलिए ऐसा ऐसा नहीं करना चाहिए. आप करके देख लो, so you will learn like this only. But I'm already giving you this input that if you go to very small size of your every finger, then what happens is that by the time you do the post layout simulation, the horizontal wires that you will need to run to connect all the fingers together, all that parasitic capacitance will actually overwhelm the overall delays.
Yes, sir.
Okay.
That I did not consider.
Yeah. Faisal?
yes, sir. Sir, I have a simple doubt. Like when we were talking about diffusion capacitance, uh, I was not able to understand the formulas that was written below it. The Cj into area plus Cj into parameter.
Yeah. So let me go to my whiteboard. That will make it easy. It will make it easy for me to explain it to you. Are you able to see the whiteboard?
Yes, sir.
So what were we looking at? We were looking at a 3D shape where we said that there is this tub,
Yes, sir.
and there is this wall, and then there is this poly that. So इस तरह का हमने कुछ देखा था, है ना?
Yes, sir.
So we said there is one kind of capacitance at the bottom, which is to be multiplied with area, and there is another kind of capacitance on the side walls.
Yes, sir. Which was multiplied by parameter.
है ना? So side walls के लिए आपको अब you already know the height of or the depth of your junction and
Yes,
or
sir.
source or drain region. So the formula was essentially that C bottom is equal to Cj into area, and C side wall, again you could have done Cj into perimeter into H.
Yeah.
We could have done that. What we did was we said no, Cj into H is equal to Cj SW into perimeter.
Okay. And so for the bottom What are we doing CJ and why are we doing the CJ into area? Can you please
So
let me
CJ
know?
is capacitance per unit area.
अच्छा फिर area से okay okay फिर
It is the junction capacitance
per unit area.
पर यूनिट एरिया। तो ये तो आपका वेस्टे में रैवी में सब में दिया हुआ है।
Acha, oh, okay, 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 sir. And so one more thing about the sheet resistance.
हम्म।
You were showing a figure when we were calculating the resistance along the length, it was 2 R naught, and when we were calculating along the width, it was R naught by 2. Can you please explain that part again?
So let us say I have this wire, only one wire,
Yes, sir.
and this is 1 square. So over here what we are saying is that, let us say this is W, and let us say this is 2.5 W.
Yes, sir.
Now let us say current is flowing in this direction.
Yes, sir.
What would be the resistance that you will see? So अगर मैं इसको 3D में बनाऊं, so this is my wire
Yes, sir.
and current is going in this direction. So what is the resistance of this? I will say I have to run 2.5 squares upon W, है ना? 2.5 squares,
So how is it 2.5?
क्योंकि मैंने लेंथ को 2.5 W बोला ना।
Yes, sir.
तो अब अगर मेरे को इस वायर का रेजिस्टेंस निकालना है, व्हाट इज द फॉर्मूला फॉर रेजिस्टेंस? रो
Rho L
L
by.
by A.
Yes, sir.
What is the length?
2.5 W.
What is A?
2.5 W into W.
है? What
नहीं
area are
नहीं
you
नहीं.
talking about?
Uh,
This cross section ना?
yeah. W into W.
W into
हाँ.
this height could be T.
Okay.
T.
Okay. Okay. Yes, sir.
So if I say rho by T is equal to R naught, then the resistance of this wire is 2 R naught. 2.5 R naught, sorry.
2.5 R now. Okay. Yes, sir.
ठीक है?
Yes,
Now
sir.
let us say that current is moving in this direction.
Yes, sir.
So now what is the length?
Length will be W.
What is the area?
T into 2.5 W. Okay. That is why. Okay. Now it is clear, sir. R naught by 2.5. Okay, sir. It is clear
ठीक
now.
है?
Yes, sir. Thank you.
Yeah. Deepank,
Hi, sir. Good evening, sir.
good evening.
Sir, I might not be able to frame my doubt, but I'll try. So, sir, initially in PN junction, when we used to talk about diffusion capacitance, we clearly had two plates like P junction and P side and N side, and between them depletion region. But here if we talk about depletion capacitance, then yeah, we have the lower a part of the tub as we can say that one plate, then the depletion region acting as dielectric, but you refuse to call substrate as the other plate. So can we assume the junction where the depletion region and the substrate are, that is the second plate of that depletion capacitance?
So let us go back to this side, this part. Let us go closer to any one part.
Yeah.
So what is happening there? At the sidewall boundary, I have doped N plus, and on the substrate, I have doped P.
Yeah. Yes.
So a depletion layer will be formed.
Yes.
What will happen? A depletion layer will be formed. N plus side पे पतली सी and P side पे थोड़ी सी बड़ी,
Correct.
because
Correct.
doping on P side is less.
Correct.
So this is your dielectric thickness.
Right.
This is your one plate.
Hmm.
This is your second plate.
Actually, I was talking about the base part when there is. I'm not talking about the N plus.
बेस
I'm
में भी
talking.
यही है. बेस में भी यही है.
Okay.
आपने अपने सोर्स ड्रेन में N प्लस डोपिंग करी और नीचे P टाइप था.
हाँ तो सर वही जो P is the substrate, so we
P
can
is a
call it
substrate.
we
हाँ.
can call it second terminal, and then sir, yeah, that's what just I wanted to
Yeah,
confirm.
yeah.
And the second thing is sir, जब when we connect poly from NMOS to say PMOS in inverter, we uh, had to make a PP or NP layer also.
Yes.
So to say that since it does not have its good conductivity initially, so we need to increase it. So I just wanted to imagine how is it would it be done real? So first the
So in
poly,
reality, there is N plus doping over here.
yeah. So actually
So
it was
what happens is it is called salicidation. So there will be N plus on one side and P plus on the other side.
yeah, yes. Oh, okay.
तो क्या
Yes.
होता है पॉली के
Yes.
ऊपर, तो अगर हम इसको सीडी पॉली माने,
Hmm.
ठीक है, सो इस बाउंड्री पे जहां पे एनवेल की बाउंड्री आती है, इस बाउंड्री पे यू विल सी देयर विल बी अ काइंड ऑफ अ, मतलब अगर आप माइक्रोस्कोप से देखोगे तो यू विल सी देयर इज दिस काइंड ऑफ ओवरलैप ऑफ टू लेयर्स हैपनिंग,
Yeah. Yes.
एंड दिस इज सैलिसाइड. This is all salicided poly. So cobalt, nickel, silicon, silicide. So है ना, तो इसी के अंदर आप जो सैलिसाइडेशन करते हो उसी के अंदर आप एडिशनल पी प्लस या एन प्लस डोपिंग कर देते हो ताकि ओवरऑल जो रेजिस्टिविटी है वो कम हो जाए.
तो ऊपर से करते हैं हम मतलब लाइक इट्स
या
पहले हम पॉलीग्रो करेंगे देन वी विल डू इट.
ड्रॉ नहीं, पहले पॉली मैन्युफैक्चर करेंगे,
ओके.
हाँ उसके बाद डोपिंग करेंगे. तो बेसिकली जब हम नीचे की डोपिंग कर रहे होते हैं ना तो पॉली की भी डोपिंग हाथ के हाथ हो जाती है.
ओके.
आपने जब सोर्स ड्रेन के लिए यहाँ पे डोपिंग करी
Yeah.
तो पॉली भी वहीं बना हुआ था ऑलरेडी, तो
करेक्ट.
पॉली की भी हो गई.
ओके. या आई थॉट हम क्योंकि हम ड्रॉ किस ऑर्डर में कर रहे हैं और हो किस ऑर्डर में रहा है दैट इज डिफरेंट. या सो आई गॉट कंफ्यूज देयर. थैंक यू सन. दैट्स ऑल.
या
दैट्स ऑल.
राघव,
Yes, sir. So, what do you mean by sir,
राघव, आई एम नॉट एबल टू हियर यू.
hello, hello, I'm audible. Hello,
बहुत स्लो आ रहा है. आर अदर्स एबल टू हियर राघव क्लियरली?
No, sir, it's very low.
ओके.
hello.
हाँ अब हेलो सुनाई दिया, हेलो सुनाई दिया, लेकिन बहुत धीरे से.
So is it audible now?
बहुत माइल्डली, बट हाँ प्लीज स्पीक.
So actually, by the dimension of a cell, you mean only the height.
By dimension of a cell I mean only the height. What do you mean by that question?
So I mean there was term written like dimension of a cell. So I wanted to know what exactly do you mean by that?
कहाँ पे लिखी थी ये टर्म राघव?
सर ये वो जो आपकी रिकॉर्डिंग होती है उसके ऊपर एक हल्का सा थोड़ा सा डिस्क्रिप्शन होता है ना, लाइक उस पे लिखा होता है वी डिस्कस डायमेंशन ऑफ अ सेल.
ओके सो अगर हम कहें तो what are the dimensions of this cell? If this is a standard cell, what do you mean by dimension of this cell?
So I mean one is height, I think I can come up with.
Okay, if you say it is height, and then
So
width
I
also,
mean,
na? That will, both of these are required to define what the cell is like, na?
okay.
मेरे को अभी भी आपका सवाल नहीं समझ में आया राघव.
So I mean I wanted to know कि मतलब आप dimensions of a cell से मतलब क्या मीन करते हैं मतलब उसमें.
Yeah, both height and to width. For height, we already talked that the height is limited to tracks. To tracks, matlab, I already fixed that this library will have 12 tracks or 14 tracks or 9 tracks or whatever. Okay. Now, width also increases only in terms of tracks. Okay. But if I need more fingers, if I need to make more fingers, I will increase the number of tracks and I will increase the width.
So can you repeat this point? I mean if to increase the width.
So just like for height, we said that there are tracks, है ना? That
Yes,
I can run 12 metals over this cell,
yes sir.
है ना?
Yes, sir.
Similarly, for the width side also there are tracks.
Okay.
It's always a grid. ठीक है? Because metal 2 is horizontal, then metal 3 will be vertical. So you cannot say that, so now this is like all cells are equal. Now you cannot say I will want to increase the height by just this much. No, if your cell is becoming this big, you have to actually go to full track width.
Okay, so but this another track width would be determined by another kind of metal 3 kind of thing.
Yeah, but metal 3, metal 2 have the same rules, no?
Okay, yeah, yeah. So actually, it
If they
was
have different rules, then yes, another metal. But typically, you will see the metals which are used just above the standard cell, metal 2 and metal 3, or if you are using other sets of metal definitions and advanced technologies, then the vertical, at least there will be one horizontal and one vertical metal with exactly the same rules which you would use to define the tracks there.
okay. So, but like when we were discussing in the previous class layout, so we said that if we like the width that was the width was part was coming depending upon how many for example, if we have a certain device, how many fingers we made, so width
Yeah,
was increasing much.
yeah,
So like when we are making fingers, we had to then basically take this consideration also.
yeah, yeah, yeah. Not, you don't take that consideration. You simply say, okay, I have to add 5 more tracks. I cannot say I will add only 5.5 more tracks. No. Even if your layout is coming till here, you have your PR boundary has to be full track.
Okay, means this horizontal along the tracks, they can be modified as per my need. The,
The width. The width can
the
be
width.
modified. The number of tracks in the width side is something that you control.
Okay,
The number of tracks on the height side is already fixed for the library that you are designing.
okay,
You control, if you are, for example, if you are in a place like ST where the entire flow is defined by them, then you could be the one who is deciding it. But if you are in some other place and someone has said, I want, suppose TSM, you are in Synopsys and TSMC said, I want 9-track library, then you know it's a 9-track library that you have to make. Then you can't change that. But number of tracks that you need in the width side, you can change.
okay. And so this information is coming from that metal DRC, right?
Yes,
Okay,
tracks is always defined by metal DRC.
yeah. And so one more thing, so what do you mean by this cell abutment, right? I mean,
So what do you mean by abutment?
it's the plain English term.
Hmm.
I mean, when we send it to me, it makes it like you were joining something or something like that.
Yes, so exactly that. I made one cell and then I made another cell and I placed them next to each other. So they are abutting each other. I had left half DRC on this side, I had left half DRC on this side. So the two structures over here are already DRC clean.
Okay. And so one more thing. So this strap, there was strap cells are nothing but those tabs, right? Only the
Yes,
substrate. So,
yes.
but like I was not able to get that why we're calling them cells. I mean,
Because they also have the same height. They have the constraint on the restriction. Like you cannot make a strap of 2 tracks. अगर आपकी 12 track library है, तो the strap cell also has to be 12 tracks because that VDD has to continue. Let us look at it like this. I suppose make uh, 3 cells in this, and I have 2 cells over here. Okay, and I say I will put a strap in between, which is not meeting the same height requirements as my other cells. So what was here? There was a VDD running here. There was a ground running here. There was a VDD running here, ground running there, and then VDD running there. But now, because आपने strap किसी अलग dimension का बना दिया, you're not, this VDD is no longer connected.
okay. So, but for this structure, we would have like two kind of cells, na? Like we had the P tap and the for the PMOS and the NMOS. So this
Yeah.
cell
So
has
आप,
both. So this cell has both, like
yes,
connected.
yes. So
Okay.
the strap cell would also have both. You will make a N well. So this is, suppose this is your cell ka template. Hmm? So you will make a P strap in this and N strap in this.
Okay, so the single cell will take care of both the kind of
Yes,
or the PMOS and the NMOS structures. Okay.
yes.
Okay.
Okay. Yeah. Gagandeep?
Yes, sir. So, sir, in the standard cell only, sir, when we make a layout, for example, so some of the DRCs are quite meaningless in that regard, if we say, because there is a minimum DRC for minimum area for n well. So, I am going to share the n well. So, there is a question of having a minimum area of n well because many standard cells would have the same n well. Uh,
Yeah, but that DRC is still required because while you're talking about standard cells, yes, there are other structures also that people would design. No? They will also make, let us say, PLLs. They will also make memories. They will make many other designs in the same technology. So the DRC still has to be defined.
so, sir, with that respect, so n-tap and p-tap putting it in every standard cell would also be mandatory, right?
Why?
I mean, on the chip level, you do
No,
not
no, no,
need
no.
that.
Wait. Standard cells are always collected and made in a kind of a wall that we were discussing. Hmm. But how do you say the same thing for memories? Or how do you say the same thing for PLLs? They are not standard cells. They do not follow the same template height that you are using.
So, sir, the projects that we make, for example, so in that you will give us some circuit. We will be.
I will give you only standard cells.
Uh, okay, so in that we have to put n-tap p-tap to at least clear
No.
the DRC.
Yes, so that you can put. You can put sideways in the side somewhere, not inside the cell. You will not count that area. Something that you're doing only for cleaning LVS and being able to extract your netlist, that you will not count in the area.
So only thing that counts to area would be within the PR boundary that you said.
Yes.
Okay.
And every part of your cell should have half DRC from the PR boundary.
Okay.
Okay?
So that PR boundary would be some kind of line that we will make on the other.
There's a layer. There is a layer called PR boundary. PR BOUNDRY something. There is a layer like that. आप अपने LSW में देखेंगे आपको मिल जाएगी.
Okay, sir. Thank you.
Okay? Yes, Gaurav.
Sir, in last class, in that NAND gate layout, you told that we have to take output from the middle portion to reduce the capacitances. Sir, I am not getting which capacitance and how they are reducing.
You tell me which capacitances are we अभी थोड़ी देर पहले भी तो हम उन्हीं capacitances की बात कर रहे थे. What capacitances come into picture when you tap something onto a drain on a source?
Depletion.
हाँ, depletion, but कहाँ का depletion?
Drain source.
Diffusion capacitance, junction capacitances, ना?
Yes, sir.
तो अभी जब हमने थोड़ी देर पहले देखा कि how is the total junction capacitance calculated, है ना? हमने that was the first thing that we picked up अभी.
Actually, sir, I joined late.
Okay, so this is the junction capacitance. This is the junction view, है ना? There is a bottom, there is a side wall, everything is there.
Yes, sir.
So at each of these junctions, चाहे वो side wall है, चाहे वो bottom है, there is a PN junction happening. Bottom पे भी PN junction बन रहा है, side wall पे भी PN junction बन रहा है.
Yes, sir.
है ना? So every junction has a capacitance.
Yes, sir.
So if every junction has a capacitance, then if you reduce the area of your source and drain, if you reduce this area, you will be able to reduce
Okay,
the
sir.
capacitance.
Okay, sir. Okay, sir.
If you reduce the perimeter that needs to be multiplied with CJSW, you will be able to reduce the capacitance.
Yes, sir.
है ना?
Yes, sir. Okay, sir.
Okay.
Got it.
Yeah. Devjit?
Yes, sir. I my question is actually answered. I had the same question that without clearing DRC, how we proceed in LVS in standard service design.
तो मैंने जवाब दिया है इसका.
Yes, sir. हाँ, sir. आपने कहा ना कि just for clearing the DRC will make the N-taps and P-taps and will not count it.
हाँ, yes.
Yes, sir. Thank you, sir.
Okay. Yes, Priyanka.
Hello, sir. I am audible.
Yes, you are audible.
Yes, sir. I have few questions. First thing is like I didn't understand what is a tap. Like it is just a isolating material between two cells.
No, it's a contact. So हमने अभी हमने क्लास में भी ये बात करी थी, यू कैन वॉच द वीडियो अगेन. सो टिपिकली क्या होता है, टिपिकली देयर इज अ पी टाइप सबस्ट्रेट in which you make n plus source and drain, है ना?
Yeah, yeah.
So what happens, there is a junction in between them, pn junction, and उसी की capacitance हम यहाँ पे बात कर रहे थे,
Mm-hmm.
है ना? So if instead of n plus I make a p plus region, what happens?
जंक्शन मतलब कैपेसिटेंस का वो नहीं होगा
There is no junction there now.
हाँ
So whatever contact I put here, whatever voltage I give here, that will directly go to the substrate. So this is called a tap or a strap. So because this is where the body terminal is getting tapped. See, otherwise you have no way to connect to the body, huh?
So basically it is used for connecting body of different cells.
It is used to control the body terminal. Whether you want to give a VDD there, whether you want to give a ground there, whatever you want to give, this is the place where you will give the body its voltage, its current, its whatever.
Okay, sir. So
That's
like,
why it's called a tap. The body is tapped here.
for different cells we use different taps, na, in same. Like you gave the example of brick in which we have different layers. So in that we are using different taps.
No, in fact, we said that the DRC says that there should be a tap every 30 microns. So I do not need a tap for every cell. Many cells will share the same tap. हमने तो ये बात करी थी प्रियंका.
Okay, I got confused with diagrams as well. And one more thing, sir. Sir, you just you said in the class like if we have to implement a capacitor with gate or with metal, so we will choose gate because it's denser. So I didn't understand the statement. Like, what does this mean?
So we discussed this also. You could review that part again. So what is the value? How do you define the value of a capacitance? What is the formula of a capacitance? Capacitance की value क्या होती है? There are two plates, P1 and P2, and there's a dielectric in between. How do you find how will you characterize what is the formula for capacitance between plates P1 and P2?
Epsilon A by D. Epsilon naught A by D.
Epsilon A by D. So what is A?
Area.
Area of the plates.
Plates.
What is D?
Distance between the plates.
है ना? Thickness of dielectric. ठीक है? Now let us say there is a gate, and I'm trying to use the gate capacitance. So what is the thickness of dielectric here?
POH.
What is the order of this?
Nanometer.
Few nanometers, है ना? So let us say
Yes, sir.
1 to 2 nanometers. Now let us look at metals. There is a capacitance between them. What is the height of this? Or what area की बात छोड़ते हैं अभी. What is the spacing between two metals? 65 nanometer में what is the DRC for metal 2?
90 nanometer.
Metal 2 90 या 100 है?
100. Metal 190.
100.
है ना? 100 nanometer. So if I have to get same capacitance, in one place thickness is 2 nanometers or 1 nanometer, and the other place thickness is 100 nanometers of the dielectric, what will be the ratio of area that I need to keep? 50 to 100 times. Are you able to see this, Priyanka? Is Priyanka here, or she got disconnected?
She got disconnected, I guess.
Oh. It's clear to all of you?
Yes, sir.
Sir, no,
See,
no, sir. Can you please explain it once again?
चलो आपको कहाँ तक समझ में आया?
Sir, ये gate oxide capacitance का this when the thickness is 1 to 2 nanometer, it's fine. But how are you comparing this to the spacing between the metals and?
So how will you implement the metal to metal capacitance? If I have to make a capacitance by using metals, how will you make that?
By spacing it with certain distance.
By spacing it with?
Certain distance by maintaining a space between two metals.
That is the minimum space. What is the minimum space you can keep between two metals?
Yeah, it's 100 nanometers.
So that is the dielectric that is coming into picture now.
Okay.
So there is plate 1, there is plate 2, and there is a dielectric between them.
Mm-hmm.
So how much area do you need? How many times area do you need now to get the same capacitance?
Okay, as the spacing is larger, it requires
100
lesser.
The Tox here was, so there is epsilon, let us say, is same. Both places are using silicon dioxide. Let us say that. So I am saying epsilon A gate by 2 nanometer is equal to epsilon A metal by 100 nanometer. So what is A metal by A gate?
So it's 50. So gate requires lesser area for achieving the same capacitance. Okay.
Is it clear now?
Yeah, yes, sir.
So we use a very basic formula of capacitance. Nothing else was there. Back to the basics, we call it.
Sir, I have one more doubt, sir. While designing the standard cells, so we don't use the P taps or the N taps. We don't place it, right, sir?
We don't place it inside the standard cells. For every row, we will place it a few times depending on the DRC requirement.
Okay, sir. So suppose if we are making a circuit and if we don't place the P taps or the N taps, so that time we'll get a DRC error, no, sir?
Yeah. So that was what we just discussed, Ranjit. We said that we will clean the DRC by placing some N tap and P tap for some time. But since these P taps and N taps will keep outside the PR boundary, we will not count those N taps and P taps in the area.
Okay. And sir, while evaluating the height of the cell, suppose we have a 12-track library and we have certain height specified. So we'll be running metal 1 and metal 2 at the top and the bottom of the in one particular row, right, sir?
Metal 2 nahi. Metal 1, only metal 1.
We'll be running metal 1 and metal 1 on top and the bottom.
Yes.
So does this also come under the inclusion of height of a standard cell, or is it excluded, sir?
So half of it will come.
Okay.
So 12 tracks. So जैसा हमने कहा था ना, so we would say, for example, that this height is 12 tracks. Let us say.
Yes, sir.
And then I will run metal over it.
Okay.
ठीक है? So I will do it like this कि at least DRC जो है दोनों तरफ meet होगा. Such that ऐसा नहीं करते इसको. So we have to ensure that minimum metal width is always there. So you put half inside and half outside.
Okay.
At least इतना आपको करना है.
So we
minimum.
Okay, sir. So I understood that this half at the top and at this half PR boundary we leave for each and every standard cell.
No. Wait. You don't need to leave this. So beneath this metal there could be devices. Na? You could make a poly run beneath this metal also. It is a different layer altogether.
Okay.
There could be an active running here in this region. What's the big deal? The width of this metal only constrains one thing, and that one thing is where can you have the next metal over here? I want to put a contact. So what is the smallest device I can make? That is what it constrains, because there is a DRC between these two.
Okay.
Otherwise, it does not change anything. Other layers will anyway move like that. So if you make a very thick metal one, then you have lesser metal one available in this region where you need to make the connections.
Yes, sir. Okay. Now I understood, sir. So this metal height is nowhere related to the PR boundary which we defined.
No, not at all.
Okay. Yeah. Thank you, sir.
Okay. Metal is just any other structure. PR boundary तो independent है, वो आपने track से निकाल ली.
Okay. Yeah. Understood, sir.
Yeah. So all questions done. No one
Sir,
has
can
their
you
hand
repeat
raised.
that denser part once again? My connection was lost, so I wasn't.
Yeah, we noticed that. So I did not remove that part. So आपने कहाँ तक सुना था प्रियंका? You were here till T-ox and T spacing between metals. Were you
No,
there till here?
you just started and I just lost.
Okay. So who will explain? We didn't realize that you were disconnected, so I had continued. So who will explain?
Sir, maybe I will explain it, sir.
Yes, Ranjit.
Yeah, suppose if we consider in the MOSFET the oxide, so the oxide would be of order 2 nanometers. And suppose if we consider two metals, there would be the capacitance which will exist between these two metals, which are separated by a space of 100 nanometers. So which is according to the minimum DRC requirement. So if we want to achieve the same capacitance with both the poly and the metal, so if we take the if we equal the values of both of them, then we can see that the ratio of the area of gate to the metal which is required will be very less when we use gate when we use the polysilicon.
आप ये equation देख पा रहे हो प्रियंका?
Yeah. Yes, sir.
A gate by 2 nanometer and A metal by 100 nanometer. So A metal is 50 times.
Yeah, sir. So basically, we are talking about area. Basically, in gate, we will be.
Density is always about area, na Priyanka?
Yeah. Okay, got it, sir.
Yeah.
So this will happen only in the case if the dielectric are equal or maybe less some. Because if we consider the water in the other case, then this is not possible because water at the different temperature have the epsilon naught ranging from 30 to 88. Na?
Yeah. We are only talking about silicon dioxide over here.
Yes, sir.
है ना? We
Then
know that
let's
gate
say-
material is also silicon dioxide and intra-metal dielectric is also silicon dioxide.
Yes, sir.
Okay, so now we have exotic intrametal dielectrics where we also have air bubbles inserted in them. पता है? So we have porous intrametal dielectrics, and then epsilon will change.
Porous
Yes.
means?
Porous means there are air pockets in between them.
Okay.
So that the capacitance reduces.
The charge is stored in that air pockets.
No charge is stored. There's just an air pocket. Because the epsilon of air is 1, whereas epsilon of silicon dioxide is 3.9. So if you use air pocket, the effective epsilon is lower. So effective capacitance between metals reduces.
Okay, sir. Thank you.
Okay. Madhur, you have a question?
Yes, sir. So, what is channel stop implant?
ये भी बात हुई थी. Channel stop implants are high doping implants which are used so that what do you say, doping doesn't go below that. You ignore that, don't worry. Channel stop implants, वो सब, you will study more of that if you take up those SSD and INE courses. And in fact, those are not even valid. Today you talk of super halo implants, and pata nahi kya kya. So it's okay.
Okay, sir. And so, why do we need to always have a OD layer when eventually we will use NP and PP layer to define where our this?
So see, अभी यहाँ पे दिख भी रही है इसी view में, but let's go closer over here. So if you do not have the OD layer, let us say, what happens? N plus and PP तो ये है ना, yellow वाला और ऊपर blue वाला.
Yes, sir.
So N plus and PP तो ये है. So do you want the device all over the place? नहीं ना? You need to say that there is an isolation. So there is a isolation between these two actives. Is it not? There is an oxide here. There is no device here. No flow of current happening in this region.
Yes, sir.
है ना? So N plus layer cannot define where the device would be. OD layer defines where the device is. N plus and P plus layer simply tell what doping needs to happen, N plus or P plus. That's it.
Okay, sir.
Are you able to see this?
Yes, sir. Sir, so that is why OD layer is, and sir, this OD layer is one single layer instead of separating source and drain. So that is done by this poly layer. So
Yes.
that separation.
That is called self-aligned process. So poly separates the source and the drain region.
Okay, sir.
इसलिए poly पहले fabricate होता है. ध्यान दो the fabrication steps that we talked about in the first few classes.
Yes, sir.
So
Yes.
poly is fabricated first, then you do the implantation.
Yes, sir.
Then something else happens.
Okay, sir.
Yeah. Yes, Sachi?
Sir, I have a question. In the class, you told that tap is not called as via, and also the M1 anvil that we use for making contacts, that is also not via, because there is a direct flow of charge in between the N and N plus region. I mean N plus and anvil. So, sir, I want to know like what is this then via actually? I have some confusion.
Via is a term used to talk about the connect between different metal layers, metal 1, metal 2, metal 2, metal 3, metal 3, metal 4. Those are called vias.
Okay.
Yeah, that is what is a via.
Okay. Okay. So,
Does that help you? You have a follow-up
sir,
question?
yes, sir. So actually, when we were making layout, then this was fall in that category of via. So I got confused, like why is it called as? Then why we are calling this as via?
What are you calling as via?
Sir, I mean, like this M1 and Will was there in the category of vias actually.
That is some way they have organized the library. That's it. Don't worry about it.
Okay.
Via, you do not call that as via.
Okay. Okay, sir. Okay.
Okay.
Okay,
If
sir.
you start calling that as via because one library that you saw organized it like this, no other company will even look towards you. They will say, "क्या बात कर रही है? Has this person gone bonkers?" Okay. VI is only that metal 1 to metal 2, metal 2 to metal 3. That connect is called
Okay.
via.
Okay, sir. Okay. Got it. Thank you, sir.
Yeah. Yes, Gagandeep?
Sir, I had a confusion about so basically there is a reason why we use high K dielectrics for smaller technologies for gate. So sir, in that I was kind of thinking that when we go to smaller technology, so basically we want more control over the gate. So that is why we wanted to shrink the TOX also, right?
We want the gate capacitance to increase.
Okay, so increasing the gate capacitance means that the charge that I put on gate should reflect on the channel.
Yes. That is what increasing the capacitance means. Yes.
Okay, so that is why I want to increase the epsilon now, so that I do not have to increase
Yeah,
TOX.
so that I don't need to reduce TOX. Yes. Because I cannot reduce TOX any further. Tunneling हो जा रही है.
Okay.
है ना?
So,
Yes.
in an extension to the Gagandeep's question only, so for example, when we are modeling the MOSFET capacitance, the transistor capacitance, we had gate to drain, gate to body, and gate to source. So, sir, these all are basically the gate to channel thing only. But like
No. Why is gate to drain, gate to channel? Gate to drain is gate to body also, in like gate to drain is gate to drain. It is not gate to channel.
sir, I mean like the GC part is basically like in a book I read, it was written as CGCS plus CGCD.
Okay, so that was where. So again, think about it like this. This is a small signal capacitance that we are talking about. So we're talking about where is the charge coming from? If I change the gate voltage a bit, where will this delta Q happen? On the source or the drain?
So, okay. So in the small signal one.
It's all small signal capacitances that we are talking about.
So I think now the source and drain is available, so it should come from there.
Yes. ठीक है?
Yes, sir.
Because earlier the source and drain were not available. When source and drain were not available, only capacitance was this between this plate and either the inversion layer or the edge of depletion. Now, since the source and drain is here, they can infuse charge immediately. So if pinch off has not happened, then both will contribute. If pinch off has happened, the drain will not contribute.
Okay. So, but like in the when we were drawing the graph of that, so in the graph, the CGCS and CGCD were referring to the two components of the gate capacitance only.
Yeah, because gate capacitance यही है ना. What is this? आप gate पे कुछ change कर रहे हो. अब कौन सी? Where is the next plate? Where is the charge change happening? Because you're only controlling the gate, so they are part of gate capacitance only.
Okay. Okay. And that's sorry, CGD was basically comprising the three part, that the contact one, the diffusion coupling, and the overlap.
Yeah, even S,
So yeah,
even
so
C, even with source, same kind of capacitance will happen.
yes, sir. So even so now I had also another question. So for example, we were placing the strap cells or at a very at a DRC kind of, yeah, and between the like two kind of strap cells, there can be many kind of standard cells.
Hmm.
But like then for example I was not able to understand that, for example, the N well for the PMOS structure, so will it be shared across the different standard cells?
आप बताओ, देखो अभी हमने क्या कहा. अभी हमने थोड़ी देर पहले यहाँ पे एक एनवेल का स्ट्रक्चर बनाया था. कहाँ गया? हाँ, है ना, बनाया था ना ये.
Yes, sir.
तो अगर इसके साथ एक और मैंने एडजेसेंट में सेल अबट करना है, तो मेरे को ये तो कहना ही पड़ेगा कि इसका जो एनवेल है, इसका भी एनवेल सेम डीआरसी फॉलो कर रहा है. तो अपने आप ही एनवेल्स ओवरलैप हो गए, ये कनेक्ट हो गए. इसके साथ तीसरा बनाऊंगा सेल, वो भी ऐसे ही कनेक्ट हो जाएगा. ये तो टेम्पलेट में ही है ऑलरेडी. So in your template, this height of n-well is also fixed, huh? Otherwise, how will you abut two cells?
No, sir. I mean, why the height is okay? No, sir. Like along the standard cell, the height is fixed. So, like, I'm not able to understand that why this height is becoming a factor for the sharing of this. How you're
No.
relating to
So
that?
are you able to see that all this n-well region is now shared?
Yes, sir. So, but the reason for this, because of that strap cell, is I have to do this.
No. Just because you have to. So let us consider it differently. Let us say one standard cell. Let us go back to the basics. Let us say one standard cell you made like this. Now you only fix the height. You did not fix n-well height. Let us say. So in one standard cell, you made n-well like this, and in the other cell, you said, I will make my n-well in between. Now, when you bring about these two cells, what happens? Just give me a moment. Now, if you abut these two cells, if I simply bring them closer, what happens? There was some device over here that you may have made.
Yes, sir.
So, do you realize there will be DRC errors?
Okay. Right.
So, n-well is also fixed. There is no other way.
Okay. And so, like the minimum DRC for the strap cell is basically, I think that is coming from because we need to ensure that the strength of that tapping is that it is because of the design or because of the thing that because ultimately we're providing a connection to the ground, right? So we have to ensure that the active in these cell is
Hmm.
being kind of provided the required connection by the tap which is placed many cells away.
Yeah. That's where we also talked about latch up in the class, na?
Yes, so that was the reason for this stab cell, right?
Yeah.
But like, why this DRC was like 30 microns? What I was asking the
So that
reason.
latch up doesn't happen. DRC is primarily technology driven, so that latch up doesn't happen.
So, but DRC is related to like fabrication thing, na? कि, okay, I can design. I should
Yeah.
develop
So
the chip.
they've put it also as a DRC because अगर आपका latch up हो गया और to fabricate सही भी हुआ होगा तो chip will not work.
Okay, 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 sir.
You have to make a working chip. So this is a deadly thing. So they put it as a DRC.
Okay, okay, sir.
In some companies, in some DKs, it may not be put as a DRC, but that doesn't matter.
Yeah, but it's a must thing. So.
Yeah. Okay. Devajit, you had a question?
Yes, sir. I have a follow-up question from Raghav's point that regarding the minimum DRC of that P strap or N strap. Uh, Sir, the minimum DRC is it defined due to the voltage that drop that could be occurring from the strap to the cell?
Yes.
Okay, sir.
Because
Yes,
that
sir.
is where the resistance of the substrate. If the substrate is highly doped, you could have more spacing. If the resistance is very lightly doped, then the substrate resistance is very high. So you'll have to have steps very often.
Okay, sir. So the VDD that you are actually providing in the strap means that should exactly reach in the cells as well with less
Yeah.
voltage.
Yeah.
Okay. Thank you, sir.
Yeah. Pranjal?
So what is the most effective method to reduce the latch up?
Putting good straps.
Sir, shallow trench isolation is also used, no?
No, but even despite that, there will be shallow trench isolation is just to isolate two independent transistors. The thing that we were looking at over here, when we were talking about कहाँ गया मैंने अभी बनाया था ना कि two transistors, there are two transistors and yeah, इधर. So I had said no, there are these two transistors and in between them there is a shallow trench implantation. So it is
Yes,
to isolate two transistors, but it is shallow. The substrate connection will still come from somewhere, na? You have to give the connection to the substrate. It will come from somewhere, is it not?
Yes, sir. Yes, sir.
Yeah. Okay, so it's all important there. Rajneesh?
Sir, the source diffusion capacitance for a particular PMOS and MOS. So the source diffusion capacitance and the drain diffusion capacitance, will they always be same?
No. किसने कहा? यही तो हमने उस दिन फिंगर एनालिसिस में भी देखा. नहीं?
Okay, sir. Yes, sir. Yes, sir.
That was what we saw, na, that we saw that the shared node had lower capacitance than the node which was on the outside.
Yes, sir. That's why we were talking.
That is where we chose that the shared node we will use for the output and the other node we will use for the supply and everything.
Yes, yes. Okay.
Hello? So it will have different capacitances.
Sir, I have one doubt, sir.
Yes,
Sir, can we go to the inverter or the two MOS which were placed?
Yeah. Just give me a moment. Yeah, this one?
Yes, sir, exactly. Sir, here we are maintaining a lot of space between the PMOS and the NMOS, no, sir. So we are wasting more area over here. So this will be so it would be advised to have both of them nearer to each other, no, sir. We can butt both of them also, right, sir?
So how will you dope? How will you dope the NVEL and the how will you dope the substrate?
Sir, I did not understand, sir.
Okay, so let us say that you make a active here and you make another active here.
Yes, sir.
You made the poly.
Yes, sir.
And now you're saying you have to make the NVELs also.
Yes.
Now what happens? What does an NVEL mean? that in this region, I will put N doping so that the substrate becomes N type.
Yes, sir.
I have to do that doping, is it not?
Yes, sir.
Then I have to ensure that in a completely different step, the active that I make falls fully within this N well.
Yes, sir.
So I have to align this N well in a completely different step.
Okay.
That is where this spacing is required. कि गलती से भी the N doping should not come into my device, into my NMOS,
Okay.
for example. So this spacing is required. That is where it is a DRC.
Okay, but I can have this as near as possible, no, sir. The substrate of this NMOS nearer to N1.
They're trying to give you the tightest DRC already. Don't worry. That is the same objective that the technology team also has.
Okay. Sir, one more thing I did not understand was that whenever we were making layouts, it was told that the poly should not be left alone because it has lesser conductivity, and so it should be
It's very resistive.
yeah, and so we should place the NP or the PP. I did not understand how it effectively
N plus,
increases.
yeah, N plus and P plus layers on a poly also mean that you will salicide the poly there. What is salicidation? That on the surface of the poly, something that we were looking at over here, we just discussed that actually. That on the surface of the poly, we will deposit N plus and P plus so that the overall resistivity is less. हमने अभी थोड़ी देर पहले ही discuss करा था. I will show you. Yeah, this was where we were discussing. So cobalt, nickel, silicide, we put other silicides also used so that the resistivity of the polysilicon is reduced. It becomes more conducting then.
Okay. So it's not something like a substrate. So on the poly we are doing this. Okay.
Poly is salicide. Even source and drain regions we salicide. So this region also is salicided at OD and N plus and OD and P plus. You will also put a salicide layer there.
Okay. Understood. Yeah.
So that when you place a contact somewhere, it still has a path to reach the channel, a low resistance path to reach the channel.
Okay. Yeah. Understood, sir. Thank you.
Okay. So anything else? Great. So thank you guys. All the best. See you on Wednesday then. Okay. Bye-bye. I'm stopping the recording.